This video is part 3 of solving equations of logarithmic and exponential type. We've studied solving exponential functions by changing the base, by using the power property, and by graphing. Now we're going to take a look at the log problems. And to solve logs, most of the time it's really easy to convert it to an exponential first, and then use all the exponential rules that we know about solving equations. If we do have a common log or a natural log, we could go straight to our calculator to be able to solve those and graph them or any other way that we wanted to solve them. But most of them will have some other base, so we'll need to convert them to exponentials. So to do that, we need to isolate the logarithm just like we were isolating the base, and then move the other pieces away so that we get the log with the base by itself, and then we convert it and change it to an exponential. And when we're converting, remember how we hopped across the pond when we were converting exponentials into logs? We do the same thing here. We know that an exponential starts with a base, so we start at the base, hop across the pond, and get b to the y. And then that's equal to, and when we hop across the pond again, we find out that it's equal to x. So remember that logs are exponents. Logs are equal to exponents. And that's why we knew that the y was going to be the exponent on b, because the log was equal to the exponent. So let's convert and see what we can do. So if we hop across the equal sign, we start with our base because it's an exponential equation we're trying to go to. We hop across to get our exponent, and then we hop back to find that it's equal to x. And when you have a problem like this, 2 to the third, well, we know what that is, and if you didn't, you could go to your calculator, but 2 to the third, 2 times 2 times 2 is 8. So x is equal to 8. In the second equation, sometimes your base is your unknown. So we still do the same thing. We start with our base, hop across the equal sign to grab the exponent, and then hop back to find out what it's equal to. And when your base is your unknown, well, then that's when we want to take the root of both sides. So x then would be equal to 7. And remember, it's not negative 7 because, again, the base has to be greater than 0. We talked about that earlier. So it's only going to be positive 7. And then in this last case, we have ln x equals 7, which if I convert it, remember natural log means that it's going to be base e to the 7 is equal to x. And that I have to take to my calculator because I don't happen to know base e in my head very easily. But second ln will give me e, and then I put my 7 in for the exponent, and I find out that e to the 7th is approximately 1096.63, which is approximately equal to x. Okay, so there we have. So what happens when we get a more involved looking log problem? Again, we peel the layers. This 5 is right next to the log. This 4 has a plus in the middle, so we have to move it the farthest thing away first. Outside layer would be plus 4 of that onion. So we have 5 log of 2x is equal to, subtracting 4 from both sides, we'd have negative 1. And if I divide by 5, because remember we want to get this log all by itself, so we have to divide the 5 off. Now we have log of 2x is equal to negative 1/5, and we can convert it. So remember, this is a supposed or assumed, not supposed, assumed 10 when it's just log. And then we hop across the pond to get the exponent of negative 1/5 equal to hop back across the pond equal to 2x. And if we divide everything by 2, we can finally get x by itself. So 10 to the negative 1/5 divided by 2, which is going to be approximately, if we take it to our calculator, so 10 to the parenthesis negative 1 divided by 5, close the parenthesis, and that whole thing needs to be divided by 2. And we find out that x is approximately 0.32. Now again, if you ever get to a case where you aren't sure, you think, looking and thinking, I'm not sure that was really right, you can always plug it back in. So we're saying that 5 times the log of 2 times 0.32 plus 4, and that's going to be approximately 3. Remember, we rounded this number, so it won't be exactly 3, but let's plug and chug and see what we get. 5 times the log of 2 times 0.2, or 32, my fault. Close the parenthesis, and then outside we add 4, and we get 3.03, which is approximately 3. So we know that x really is about 0.32. Doing this problem, we're ready to just, it's got an involved argument here. What's inside the parentheses is rather involved. But remember, it's a log, so we have a base of 10. Hop across the pond. We have 10 cubed. Hop back across the pond to see what it's equal to, which is 2x minus 7. And then peel the layers again, because now we're trying to solve for x. So 10 to the third, and this was minus 7, so we're going to add 7 to it, is equal to 2x. And then we're going to divide everything by 2, so 10 to the third plus 7 divided by 2 will be equal to x. With 10 caret 3, and then make sure we come out of the exponent, plus 7. And I'm going to do this in 2 parts. So plus 7 gives me this divided by 2. And I get 503.5. Again, to check it, if I really needed to check it, I could ask for the log of 2 times 5.0, or 503.5 minus 7 equal to 3. So log of 2 times 503.5, and then minus 7 to multiply and then subtract 7, and I get a 3.